Hello everyone, I'm Fourre, and I will present you my solution for an automated Muskmelon counting in a real farm environment using YOLO V11 Nano. And first, a short introduction. Computer vision has the potential to transform agriculture by enabling farmers to monitor crops. It will help them to make data-driven decisions and optimize harvest timing. An example, computer vision could boost the yields of fields by lowering the losses with early disease recognition and maturity recognition. But for this, we have a few problems. First, farms are very complex and a non-uniform background. These backgrounds are very noisy and with a lot of details and other things in the background. But also, leaves and fruits can obstruct each other from time to time. This means that due to this, we have a risk of double counting or to missed a detection. For our base material to this solution, we took a video recorded by an automated guided vehicle inside a real greenhouse. This video shows a lot of challenging conditions: occlusion, variable lightnings, and a cluttered background with multiple rows of plants. We only want the first row of plants. In this first row, we have to find 73 melon, and the video is 1 minute 29 seconds long. This video will serve as training and testing materials for the melons. It will demonstrate the practicality and adaptability of this approach for real farm environments. We have a few goals for this. First, we want to recognize the Muskmelon in a greenhouse. We want to track them, we want to count them, and we want an occlusion resistance for this system. We have tested a few annotation methods in different datasets. Each dataset was made from the previous video and with 187 images. On these 187 images, we've augmented a few of them with various effects of brightness and exposure to enhance the use cases and to augment the number of images to 448. In the first dataset, we've made annotation of all the melons regardless of depth and occlusion. While in the second dataset, we've made annotation only of the melons in the front row, and these melons need to be present at least more than 50% on the images. On the third dataset, we've tried two categories annotation: front melons only for the front row, and real melons for all the other melons, and we tried to put a distinction in these melons. For the processing, first we use RoboFlow. RoboFlow is a cloud-based solution, and it will take our video and send each frame to a RoboFlow that will process it and send the result back. But due to be a cloud-based solution and due to a limitation in the plans we had with RoboFlow, this process wasn't useful and had to be discarded after. For the three other processes, we use ultralytics. This means this was compute on a local machine, and the first process was ultralytics detect that will detect all the melons on each frames. The third process will add tracking. This means each melon has a unique ID. But because each ID is unique, if tracking is lost on a melon and it reappears later in the video, it will lose this ID and have a second ID. This means we have a lot of duplication. For this, we have the last process, number 4. It uses ultralytic solution with the line counting tracking. This This method is better for duplication. We have almost zero duplication, but we have a few downsides, like we have less occlusion proof. If a melon is obscured by a leaf when it crosses the line, it will not be contained. For the results, we can see that our ground truth of 73 is almost achieved when we use the second dataset with the last process. These results are 71 melons, which is very close to 73, an error rate of 2.74. But for the speed, it's not as good. Like for the first process, which is RoboFlow, it's more than 50 minutes to compute a video of 21 minutes and 29 seconds. For the other process, they are very close to each other, but our best shot, the second dataset with the fourth process, need 153 seconds to compute, which is the double of what we have. In conclusion, we have a few strong points. We have a low error rate, 2.74%, and it can be used in a non-lab environment in a real farm. But it has a few weak points. It's not fast enough for real-time processing. Right now, we can only use this solution after we have recorded all the video, and it's not fully occlusion resistant. This is why, for the next iteration, we need to focus on a faster processing and a better occlusion resistant, but it's already quite good. Thank you for studying me. If you have any question, you can ask them to Dr. Oy.